Consider this system that might be a collection of water vapor trapped in a cylinder. A chemical system like this has an internal energy represented by the symbol U, and this energy consists of the kinetic energy of the molecules themselves, so the movement of the molecules, movement through space, also the vibration or rotation of the molecules. And the internal energy also contains the potential energy associated with the arrangement of the molecules. So how the molecules are arranged with respect to each other, and also how the atoms are arranged within the molecules will affect the internal energy. Now, a system also has what you might call external energy. So if I were to take this cylinder full of water vapor and put it up on top of a mountain, the whole thing would have additional potential energy. Likewise, if we were to take this cylinder and just throw it through the air, it would have additional kinetic energy of motion. But those parts of the energy are external to the system, so they're not associated with the arrangement and energy of the molecules themselves. And so, although external energy is important, it's not really relevant to studies of chemistry. When we're interested in changes in matter, we're interested in the internal energy of the molecules in a system. Now, the internal energy of a system can change for a variety of reasons. For one thing, heat can flow in or out of the system from the surroundings. So if you were to apply heat to the cylinder, that would add to the energy of the system, would cause the molecules to move faster. And then you can also affect the energy by doing work on the system or by the system from the surroundings. And so work is application of a force over a distance. And so the a typical example of that applying to chemical systems is the work of compression. So if I were to squeeze on the piston on this cylinder and apply a force over some distance, that work that I'm doing would also add to the energy of those water molecules. So both heat and work affect the internal energy of a chemical system, and the sign convention is that positive values of heat and work refer to increases in the energy of the system. And so the total change in internal energy is equal to the sum of the heat going into the system plus the work being done on the system. And if heat were flowing out of the system, then the heat would be negative. If work were being done by the system, if the system were expanding and pushing back the surroundings, then the work would be negative. But the point is, the heat and work both affect the internal energy of a chemical system. And I want to take a little bit of a closer look at this work term associated with compression and expansion of a system. So I'm going to take my cylinder and just rotate it, make things a little bit easier for myself. And we're going to imagine that we are applying an external pressure across the area of this piston, and we're pushing it down, compressing the water vapor that's in the cylinder. And so we are applying a force over a distance to do this compression, and the work associated with that, the force divided by area is pressure. So what you may be familiar with pressure in units of pounds per square inch. Pound is a unit of force, square inch is a unit of area. In the metric system, the standard unit of force is the Newton, and the standard unit of area is meters squared. 1 Newton per meter squared is a unit of pressure that's called a Pascal. And so if you've got a pressure that is applied across an area, the pressure times the area is equal to the total amount of force that's applied to that area. And so in the picture that I've got here, the external pressure is applying across the area of the piston and exerting a force equal to the pressure times the area. And if we imagine that we are doing this compression very slowly, then the pressure of the water vapor within the cylinder is always going to be close to the external pressure that we're applying from outside. So again, as we are compressing, we are applying this force over a distance, and so the amount of work is going to be the magnitude of that force times the distance, and that's going to be equal to the pressure times the area times the distance. So force times distance is work, and the area of the piston times the distance that it's moving. If you think about it, that the area times the distance is equal to the volume that the system is being compressed by. So the area times distance is equal to the change in volume of the water vapor here. The water vapor is being compressed, so the change in volume is negative, but the work that's being done is positive. We're doing work on the system, and it's causing a negative volume change, and so the work is equal to the pressure times the negative of the change in volume, or symbolically, the work is equal to the negative P times delta V. And I'm going to stop this video at this point and continue in the next part.